this video, we're going to talk about strain energy. The reason we're talking about strain energy is we're going to use strain energy to understand the deformation and slope and stress within different materials. Starting with Castigliano's method, we're going to, in a few lectures, we're going to talk about the Rayleigh-Ritz method for determining the deformation within structures. So, for strain energy, and the great thing about these methods is that you can use them to solve statically indeterminate problems. So if we have our stress element here, alright, and we apply an axial stress, okay, we can think of this this element as being under as a spring. So the total force being applied to the spring we can think of as the stress times the cross-sectional area here. Right. And then the displacement of our spring we can think of as being the strain along the x direction times delta x, or the original length. Right. So we can denote that the work on the element as being equal to 1/2 F times delta x. What we end up getting is we get 1/2 times the stress times the strain times delta x, delta y, and delta z. Alright, so that delta x times delta y, delta z, that's our volume of our element. So so if we divide by our volume to the other side, what we end up getting is we get that our work per unit volume is just going to be equal to 1/2 our stress in the x direction times our strain in the x direction. Okay, so so if we assume that the material itself is 100% elastic, so what that means is that there's no energy is lost due to the applied stress. The work on the element increases the potential energy of the element U. So what we mean here is if we look at our stress strain curve, right, for a material, right, in the region, in this region here, if you had let go of the material, or you let go of your stress, it would return back to the original state. There'd be no remaining strain in the material. So this is our elastic region. So as long as we're in this regime within our stress strain curve, we can assume that this theory will hold. So we can say that our potential energy would be equal to the work applied to the element, which would be equal to 1/2 sigma x epsilon x. So if we plug in Hooke's law, and we say, because it's in the elastic region, we can simplify our strain energy down to just the stress being applied squared divided by the elastic modulus. Okay? So we can sum up. We can calculate the strain energy when we have multiple stresses being applied to our stress element. So in this case, we have triaxial stress. We have sigma x, sigma y, and sigma z. All right. Using the stress-strain relationships we've established in Chapter 1 and during the first few lectures of the course, we can plug those in and we can get the total potential energy due to our normal forces due to sigma x, sigma y, and sigma z, but also in terms of just the elastic modulus and v. So we've eliminated the shear terms from this equation. Okay. So in a similar fashion, shear stress can also create strain energy within a stress element. So if we start out with an undeformed element and we then add a shear stress to it, that shear stress is going to cause a shear strain, gamma xy. So we again can define work as being equal to 1/2 our force times our displacement. So our force in this case would be equal to the force over the applied area. So in this case, our applied area would be the top of our element. So that's going to be delta x times delta z. Alright, and then our displacement is going to be equal to this distance here, which is gamma xy times delta y. Alright, so if we rearrange the equation, we can put all the volume terms on one side and we have our stress and shear terms on this side. We can again divide by the volume and assume the material is elastic. So if we do that, we end up getting that the shear energy due to the shear strain is equal to this equation. So we can again go to a case where we have multiple shear stresses acting on the element. So if that's the case, I'm skipping it. I'm getting ahead of myself here. First we could do is we can substitute for gamma xy using the elastic modulus and the Poisson's ratio to get this value of our shear, for our strain energy due to shear. We can substitute in this equation. So if we go to the overall general state of stress, where we have 6 unique components of stress, we can say that the total shear energy or strain energy is due to the strain energy due to normal force, normal stresses, and the strain energy to shear stresses, which would be this following equation here. So you could rewrite it in this form here. So if you plug in the stress-strain relationships or the strain-stress relationships, you can get this equation down here. Alright. Now, in the cases that if you know the principal stresses within your stress element, this equation simplifies down to just the following equation here. Alright. And then we can keep going in the cases where you have no stress in the z axis, sigma z, tau z yz, and tau zx. The strain energy term can simplify down even more. And then if you had the principal stresses, but one of your principal stresses is equal to 0, you would get this equation here. Okay, so that's how. So using these equations on the bottom for any state of stress that you're given, you can calculate the total strain energy within a stress element for any given loading situation.